Now let's discuss about Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Look at this setup. This is a strong bar magnet which is moving towards the coil. Strong bar magnet moving towards the coil. If this is a strong bar magnet, so its lines of forces we can draw. This is the lines of forces. When this magnet is moving towards the coil and it is slowly entering to the coil, density of these lines of forces is increasing over the coil. Now we know that the density of the lines of forces is known as flux. So because of flux change, a instantaneous EMF will develop in the coil. Because of the EMF, a current will flow through the coil. That current can be identified by a galvanometer which is attached to the coil. Here, if the bar magnet's N side is moving towards the coil, now because of the huge flux change, an instantaneous current will develop. When the N side moves towards the coil, the direction of current is anti-clockwise. This is anti-clockwise direction. The current will flow in anti-clockwise direction. We can identify the current, presence of the current, by use of the galvanometer. So as a Faraday's law, we can say that the instantaneous EMF is nothing but change of flux d phi by dt. So rate of change of flux will create the EMF in the coil. The rate of change of flux will create the EMF in the coil. Now if there are n number of coils, then we can multiply this equation with n. Then we'll get the EMF value as n d phi by dt. Now look at the second scenario. When the bar magnet is moving away from the coil. When it is moving away from the coil, in the same process, the lines of force will decrease in that case. It will minimize in that case. So in case of decreasing electric flux, that is also one kind of rate of change of flux, which is also create an instantaneous EMF in the coil. That's why you use a negative sign over here also, because rate of decrease of electric flux is also creating the instantaneous EMF in the coil. Here also a current will develop in the coil that we can identify through the presence of the galvanometer in the coil. Look at the current direction over here. When N side is coming towards the coil, the direction of current is anti-clockwise. When N side is moving away from the coil, the direction of the current is clockwise direction. It is in clockwise direction. So there should be a relative motion between the coil and the magnet. Then only the EMF will create over here. We can say if this is the coil, and if S side also moves towards the coil, that time also it will create a magnetic, that time also it will create an instantaneous EMF. If N side is moving towards the coil, it is anti-clockwise direction. So here at that time, it will be in clockwise direction. Current will be opposite of this. Same thing, if S side is also moving away from the coil, again an instantaneous EMF it will create. At that time, direction again will change. Now think, if the magnet is fixed and the coil is moving towards the magnet, that time also a current will be generated in the coil. If both of them are moving, both, this is also moving, this is also moving, suppose its velocity v1, its velocity v2, and if v2 greater than v1, then also a EMF will be generated in the coil. That means there should be a relative velocity between the coil and the magnet. Okay, so there should be a relative velocity between the coil and the magnet. So look at the all cases. Here the coil is fixed, magnet is moving. Here also the coil is fixed, magnet is moving. In the first case, north side is moving towards the coil, so current direction is anti-clockwise. Here north is moving away from the coil, so it is clockwise direction. So Faraday's law says that the change of flux, this is my change of flux, d phi by dt, this is in calculus format. EMF will be d phi by dt. If n is the number of turns means if there is n number of turns, n number of coils over here, then E will be n d phi by dt. Why the minus sign? This minus sign is coming from if there is rate of change of flux is negative, that means if decreases, then also it will create an EMF. If H side moves, then also, if S is moving away, then also it will create a magnetic field. Look at this part. Here its velocity is 0 and coil is moving with a velocity. Here both of them are moving with different velocities. Coil also moving, magnet also moving. If I say V2 greater than V1, there should be a relative velocity between the coil and the magnet, then only the EMF will generate. Come to this, a little problem over here given in calculus format. Very interesting problem. Look at this one. Here the flux with respect to time is given. The change of flux is given with respect to time. And they're saying that at 3 seconds this flux change is happening. Where the coil has a resistance of 5 ohm, we have to calculate the current. Now come to the solution part. What we're doing. Look at this one. So phi is 2t cube plus 4t square plus 8t plus 8. If I differentiate this one with respect to t, what I'll get? d phi by dt. Here 2 constant outside, derivative of t cube, 4 constant, derivative of t square, 8 constant, derivative of t only, and the derivative of this 8 is nothing but 0. It is a constant term, as we know from calculus. So this d phi by dt is nothing but EMF, as we know. This is 2 into, look at this part, is t cube, so it will be 3t square, and this is 4, and this part is t square, so it will be 2t plus, and this part t in this 1. No, from the calculus formula, the basic calculus. So phi become 6t square plus 8t plus 8. This is my EMF generated in the coil. Now when t equal to 3 seconds, and it is given, look, t given, t equal to 3 seconds. T is 3 seconds. If I am putting t equal to 3 seconds. So my EMF is coming 6 into 3 square, 8 of 3 plus 8. How much I am getting? It is 3 square 9, so 54 plus 24 plus 8. So we'll get 86 volt. Clear? Now we know that EMF is I of R. This is nothing but Ohm's law. Ohm's law. Now this is 86 and its resistance also given we have, that is 5 ohm. Put the value. So this is I and 5. So how much current I'll get? 86 by 5. That is nothing but, if you calculate, it will come divide. No? So just divide the value, this much of ampere current it will generate. So I have given 5 questions from the sections as your home assignment. Please go through that one and try to do it. And I have given 2 numericals based on the simple concept of electromagnetic theory. Try to do that also. So what we have learned from the section, we have learned that what is electromagnetic induction, what is flux, and the basic concept of Faraday's law of electromagnetic induction. Thank you.